Welcome to This Explainer. Today, we're going to unpack the fascinating rules of chemistry that govern our everyday lives. Seriously, we interact with these scientific principles literally all the time, usually without even realizing it, right in our very own kitchens.
Okay, let's dive into this by starting with a super relatable problem I'm sure we've all faced. You pour a nice cold glass of iced tea, add a spoonful of sugar, and no matter how intensely you stir that glass, you're left with this gritty pile of sweetness just sitting at the bottom. Or, you open a bottle of soda, leave it out on the counter, and come back to a completely flat, lifeless drink. Why exactly does this happen? Well, the answer lies in the science of solubility.
So here is our roadmap to understanding and controlling these invisible chemical reactions. First, we'll hit the basics of solubility. Then we'll look at soluble versus insoluble materials, followed by solubility versus dissolving rate. After that, we'll explore the 4 key factors at play and wrap up with some real-life applications. All right, part 1, the basics of solubility.
To actually manipulate these reactions, we need to quickly align on the main players here. The solute is the substance that's getting dissolved, like your sugar. The solvent is the liquid doing the heavy lifting, which is usually water. When you combine them perfectly together, you get a solution, which is just a seamless, homogeneous mixture. So solubility itself is simply the ability of that solute to dissolve in that specific solvent. When you drop distinct solids, like salt or sugar, into a liquid solvent, they don't just vanish into thin air. Actually, they break down at a microscopic level until they blend into a perfectly clear solution. The solid hasn't disappeared from existence, it's just been broken apart and distributed completely evenly throughout the liquid. Moving on to part 2, soluble versus insoluble, or what can and cannot mix. There's a really stark contrast in how different materials behave. Soluble materials, things like sugar, salt, and powdered orange juice, they integrate beautifully into water. But insoluble materials, think sand, pebbles, or even plastic bottle caps, they just sink like a stone. Honestly, no matter how hard you mix them, they completely lack the chemical ability to interact with the solvent and form a solution. All right, part 3, solubility versus dissolving rate. This is actually a super common misconception. We have to strictly separate the amount of a solute that a solvent can hold from the speed at which that solute actually breaks down. Solubility is all about capacity. It's the absolute maximum limit of how much solute can fit into the solvent before it just gives up and starts piling up at the bottom. Dissolving rate, on the other hand, is basically just a stopwatch. It's simply how fast the process happens. Different conditions affect these two things very differently. For instance, increasing the temperature can boost both the speed of dissolving and the total amount that can dissolve. But what about stirring or changing the particle size? Well, those actually only affect the stopwatch. Keeping that distinction in mind is an absolute game changer for mastering these mixtures. Let's jump to part 4, the 4 key factors you can actually control. Think about making your morning coffee or tea. What happens when you add sugar to a piping hot mug versus, say, a glass of ice water? Heat is our first major lever here. A hotter solvent dissolves a solute way more effectively because heat literally gives the particles more energy to move around and collide. Because of this extra energy, hot water can hold a significantly larger total volume of dissolved sugar than cold water ever could. And that right there is exactly why your iced tea leaves a gritty mess at the bottom. The cold water simply hits its maximum capacity much, much sooner. So what happens when we try to force the issue? We all instinctively grab a spoon and stir our drinks when we add something to them, but what is the science actually doing here? Okay, let's dive into this because it's fascinating. Stirring does not change the maximum amount of sugar the water can hold. It only affects the dissolving rate. You see, when a pile of sugar sits at the bottom of a glass, the water immediately surrounding it gets completely saturated. By stirring, you are constantly sweeping away that saturated water and bringing fresh, empty solvent into direct contact with the surface of the sugar. It speeds up the rate tremendously. But once the solvent is completely full, no amount of stirring is going to make more sugar dissolve. Now, let's think about the physical shape of our ingredients. If we take a densely packed sugar cube versus loose granulated sugar, how does the water react? This race comes down entirely to surface area. A solid cube only lets the water touch its outside walls. But when you break that cube into thousands of loose particles, you expose massively more surface area to the solvent all at once. It doesn't change the total capacity, but it definitely gets you to the finish line a whole lot faster.
Let's step away from solid solutes for just a second and look at the gas dissolved in your favorite soda. The rules kind of change a bit when we're dealing with gases. The absolutely crucial point for gases is pressure. This is our fourth factor. Unlike solids, gases are highly sensitive to pressure. A sealed bottle of soda is bottled under intense pressure, which literally forces the carbon dioxide gas particles to compress and dissolve right into the liquid. They're trapped in there. But the exact second you unscrew that cap, the pressure drops rapidly to match the room. Without that high pressure holding them in, the gas particles immediately escape the solution, form bubbles, and just rush to the surface.
Let's bring this home with Part 5, Real-Life Applications of Solubility, in action. To quickly summarize our chemical toolkit, heat fundamentally changes the maximum amount of a solid that can dissolve. Stirring and shrinking the particle size are your speed controls to make things dissolve much faster. And finally, applying high pressure is exactly how we force gases to stay dissolved in liquids. It is so fascinating to realize that these principles govern almost everything around us, well beyond the chemistry lab. I mean, solubility determines how effectively a powdered medicine enters our bloodstream. It's exactly why brewing hot coffee extracts way more flavor than cold water, and why hot water and agitation allows soap to break down grease on your dishes. Every single time you cook, you're directly manipulating these rules. You are now officially equipped to control the chemistry in your very own kitchen. You know exactly how to maximize capacity with heat, speed things up with stirring and surface area, and trap gases with pressure. These invisible forces are entirely in your hands now. So the only question left is, armed with this new knowledge, what are you going to experiment with first?